Hi, everyone. Welcome back to Bufnagle the podcast, where we explore entertaining and enlightening discussions of the adventure of life and all things good. From science and technology to history and philosophy to leadership and success. We hope to give you a better understanding of the world and skills for everyone to pursue their own adventure.
Ladies and gentlemen, boys and girls, children of all ages, welcome back to Bufnagle the Circus, or Bufnagle the podcast, depending on the topic at hand. I'm Harry. I'm joined here tonight by Rafe, or morning, or afternoon, or wherever you may be on this planet, or if you're listening at the ISS, welcome. Rafe, how are you doing tonight?
Hey, I'm great. We are going to dive into a thing that I've wanted to do for a long time and have only recently had the time to actually think about how to take the time to do this, and that will become the pun there will become evident as we move along. But hey, I'm great. I'm doing great, and this should be very interesting as we get going here. But before we do that, I want to thank our listeners. Because of them, we are a global top 10% podcast. As usual, you and they can reach us at bufnagle.com. Remember to share the love, share the joy, share the buff. Tell your friend to listen, and you will get a free episode. And remember, hit the 5-star review, give us a like and a smiley star, and send us cookies, all those sorts of things, and make us all happy. And that will be good for us, and that means it will be good for you. Harry, did you took physics like in high school or college or both?
I took a physics course in high school and college, Newtonian physics.
Just one course?
So probably 2 courses in high school, if I remember. And then I had 2 semesters of physics in college as well.
Really? Okay. So you did like you said Newtonian physics?
Yeah,
right?
basic Newtonian physics, and then the second half was more, kind of along this same topic, but more optical types of physics.
Yeah, like lenses and mirrors and
right.
Focal. Yeah. Okay. Well, we're going to Well, let me ask you this. Tell me, like, what do you know about the speed of light? And like,
it's really fast. Zoom.
It is zippity doo-dah fast, but it's not infinite.
And no, it's not infinitely fast. It doesn't. It is the cosmic speed limit, right? That's a general statement that you can probably make about it.
Mm-hmm.
It is equal to what equals mc squared. So c is going to be the square root of energy over mass.
Well, that's one way you can look at it.
There you go. So it's related to mass, right?
Yeah. Well, it's related to mass when you do the energy mass conversion thing. But you're right. It's the cosmic speed limit. And we used to make the joke when we were even more geeky in high school. We would say 3 times 10 to the 8th meters per second. It's not just a good idea. It's the law. Is what we would say.
Wow. I'm sure you got all the girls with that one.
Well, look where we are today. Well, this question that we started with is this goes way back. Aristotle talked about the speed of light, and they've been talking. People recognized that there was a question about whether it was instantaneous or not, and how do you do that? And I've been reading a lot of stuff, and I've been watching tons of videos and reading a lot of stuff. And if you're listening to the Buff, I'm doing the hard work, so you don't have to. All you have to do is listen while you drive, or mow the lawn, or go for a walk, or whatever it is you do while you listen to the Buff. And we give you all the answers here that you really need to know. I found a set of great notes, Harry, from a guy at the University of Virginia named Michael Fowler. He's like professor emeritus or something like that. So he's taught lots of people. And as you get older, you come up with better ways to discuss these things. And he's got some really great notes. And you could spend hours and hours and hours doing that, or you can just listen to us.
Oh, and, sounds like a pretty easy decision, right?
And I'm not going to read you the notes because that would be cheating. We don't like cheaters. But there are times I'm going to quote directly from what Fowler says because he says it so well. So, okay, the first question, I guess the place to start is with, like you said, when you took your physics stuff, you talked with Newtonian physics with, falling rocks and
how fast does something fall when you throw it into the air, depending on what the gravitational constant of the body and how big it is, right?
Yeah.
How do two masses interact with each other?
Yeah, and there's a couple of basic formulas you get from that. Pretty much everything starts with F equals ma, and then the gravitational law and those kinds of things. But what comes out of that as you go through the first semesters of Newtonian physics is this general statement of what's called relativity. And the basic statement of relativity is that the laws of physics are the same in all inertial frames of reference. Okay,
so you got to break that down.
Yeah, I got to break that down. Okay, so let's look at that in terms of the Newtonian mechanics stuff that we were talking about. So a frame of reference, when we talk about that, it means that we have a set of coordinates. We have an X and a Y and a Z, because we live in 3 space. And then we have a clock. We have a T. So we have, I guess I think of it as a grid and a clock. So if I'm standing on my front porch, I can figure out I can draw an X and a Y orthogonal to each other and a Z that goes straight up. And I can stand there with a stopwatch and I can measure cars going by or kids throwing a baseball or whatever it is. I can map that out. And that's my frame of reference. But you could have a different frame of reference. You could be like sitting inside a boxcar on a train, and you could put a grid on the floor and up the wall, and you could have your clock too there, and you would have a frame of reference. And an inertial frame of reference is a reference frame where Newton's inertial laws hold, right? So the inertial law is that if you are in motion or at rest, you will stay in motion and at rest until an unbalanced outside force acts on you, right? You'll keep doing what you're doing until something makes you change, is really the idea. So if you are a soccer ball sitting on the field, you will sit right there until an unbalanced force acts on you. And typically it'll be somebody's foot, right? And then you will will accelerate, and you will do all sorts of things like that. So there's a couple things on that. Is you will, but the other piece is that if you're in motion at a certain velocity, you will stay in motion at that velocity until something outside pushes you. So it could be friction, like with the air or rolling across the road. It could be a force from the side to change your direction. So velocity is it has an arrow on top, right? It has, forces have arrows. They are vectors. They have magnitude and direction. And so I got to stop right here because I had this friend, who worked for CDC, and he worked in vector-borne illnesses. So like,
I know exactly where this is, but I'm sure the listeners would like this. Yeah.
So he worked at CDC, and he works in vector-borne illnesses. And a vector-borne illness is an illness that's carried by a thing. He studies plague, actually, and plague is carried by fleas, and typically these days it's carried by prairie dogs that carry the fleas that carry the plague. So the vector is the flea, and he said, we all learned in physics that vectors have magnitude and direction, but we never dreamed they could harbor disease. So that's his running joke in the vector.
You just got a little arrow with a whole bunch of fleas jumping on it.
Yeah. Yes, arrows carry disease. So vector-borne illnesses do that way. So that's how motion works in regular Newtonian land. And you will keep, like I said, the important thing is you will keep doing what you're doing if you are an object in motion or at rest until an outside unbalanced force acts on you. And that can take a lot of forms. Typically it's somebody pushing you or pulling you or hitting you or dragging you. And like the soccer ball sitting on the soccer field, there's essentially 2 forces on that. There's gravity pulling the ball down, and then there's the force of the field pushing the ball up. And because those things balance out, the ball doesn't move. But if the ball is rolling, the things that will slow it down would typically be friction or a wall or a foot.
Or wind or something like that.
Something like that will move it. Okay. So those are inertial reference frames. So if that stuff behaves in that world, then you're an inertial reference frame. Now, there are some non-inertial reference frames, and the classic one is, well, we used to call them accelerated reference frames. So when you are undergoing an acceleration, so either a change in direction or in magnitude of your motion, then things get wacky in that reference frame. So if you were sitting on that little carousel in the park, right? You take Scotty to the park, all right, and you put her on the carousel and you spin her around, right? And she has to hold on because otherwise she's going to get thrown off by this centripetal force and all that kind of stuff. But if you're riding on the carousel and you throw a ball directly across the carousel, well, the ball, once it leaves your hand, it's now in a inertial reference frame that sitting there in the earth. But Scotty's going around the corner, so the ball, you can actually throw a ball to yourself on the carousel if you throw it, if you throw it properly, you can throw it up in the air and catch it on the other side as you go around. Okay, that's an inertial reference. That's not an inertial reference frame. And the other classic one is the elevator, right? So you're on the elevator and it's not moving, and then you jump up in the air and then it moves and you feel like you're falling a whole lot. So things are wacky because you start accelerating. But once you're in
reference to the elevator, you're only at the same distance.
Right. But as long as you're not in the place where the elevator is moving, is accelerating, it's not at constant rate. So most of the time we work in inertial reference frames, but occasionally we don't. Like when we are accelerating, either like going from 0 to 60 in a car, or we're in a rocket going to the moon, or we are spinning around on the carousel. Those are not inertial reference frames. So the thing that matters is what are these laws of physics, and how do they, if you are in one inertial reference frame and I am in a different inertial reference frame, then if I watch what you're doing, I can map your actions to my reference frame. Right. So if you are in, like you said, you're in the boxcar on the train rolling at constant velocity past me on the track, and I'm just standing there, and I watch you throw a baseball, or I watch you run back and forth, or jump up and down, or do a basic physics motion thing, then the laws of physics that I see about your setup are the same as the ones that you see. The only difference is that they've been kind of translated based upon the motion. Okay. But the laws still behave. Everything still works out. So these laws are what? They are things like F equals ma and all of its derivatives. And that there's a pun in there that was deliberate, because you take derivatives of these things and you get all the other laws of motion. So if I measure the x, y, z, and t in your reference frame, and the x, y, z, and t in my reference frame, we can get them to line up, and then all the physics matches up the same. So we synchronize our clocks. So then your t is equal to my t, and that's fine and dandy. And then any position that I'm measuring for you is, well, it's your position plus v times t, which is velocity times time, which is position. Yep. Right. So that it just shifts the position as a function of time. And what's interesting is if I measure you relative to velocity, or you measure me relative to velocity, it's still going to be the same. It's just going to be backwards, negative, positive.
Right. Yep.
Right. So you're either going past me at positive v, or I'm going past you at negative v. It doesn't really matter which way you look. You can imagine, if you're in the boxcar rolling down the track, you can imagine that you're standing still and I'm moving.
Yes.
And it stays the same. Okay. And there's lots of great car commercials where two cars are driving side by side and you do things back and forth between the cars, because relative to each other, they are not moving.
Right.
Okay. So the clocks can be synced up. The positions are only off by v times t. The velocity is the same. Yep. Right? Except that it's opposited, right? Because one way or the other, it goes one way and then the other way. And that's the same, because you just take the derivative position and that's all you're left with is v. And then there's no rate of change of velocity, because you're both moving at the same velocity. So there's no
so it's all canceled out to zero.
Yeah. So everything matches up. So these are the laws of physics, and this is what you would expect to happen. This is what we learn. Now, sometimes it takes a little time to get to this. Like if you're a kid in a car and you're driving down the highway and you drop a baseball, just drop it straight down out of the car. The question is, this was always the question when we were little kids. We wondered, when we spit the piece of gum out the window of the car, does it roll forward or does it roll backwards? And what it does is it rolls forward, because it maintains the momentum of the car until unbalanced forces act upon it, and wind, gravity, and whatever cats along the side of the road eating gum. Well, that stays the same. So all that lines up the way we'd expect it to do. And that works great in the wonderful world of regular Newtonian physics and physics labs and baseballs and horses and artillery shells and trains and even simple rockets, and even going to the moon. You can do all that with just regular run-of-the-mill Newtonian classical physics. But when you start talking about light and light speeds, then things get a little weird, and you got to make your way from relativity to Einstein's special relativity. And that's where we're going with all of this.
It's special.
It is special relativity because it does things that it's just, Harry, it's mind-boggling what happens.
Things get difficult when you start moving really fast.
Not only that, it is difficult to conceive in your head what it's really doing. And I think we're going to get a little bit, not today, but we're going to get more of it next time, that light is not a particle. It's not like a little BB or a series of little BBs that are flying through the air. You can think of photons, and some experiments talk about photons in that way, but they're not. But that's the model, right? And they're not little BBs. And then some people say, well, it's wave-like, and it is wave-like. It behaves in it refracts, and it gets, and it propagates and additives, and it cancels out and adds up just like waves do. But there's nothing. But light can travel through space where there's no medium to wave. So it's not the same kind of wave as like if you snap a rope or if you move water. So that it's a nasty piece of the world, and I still don't have my head completely around how to think about it other than following the rules that are in the written down laws and making them work out. So,
well, good thing you don't have to. We're just here to explain in very layman's terms how light works.
Yeah, and this is a thing that we're going to find out that light is just like radio waves. And just
for now, yep.
Yeah, and we're going to find that out, and we're going to see. I have a picture in my head now, a little bit clearer than I had it even 3 days ago. And I spent like this morning. It's helpful. It's helpful to do if you want to understand this kind of stuff. It's helpful to do a couple fundamental things. One, turn off all external stimulation that is like movies and radio, and
other than listening to the buff.
Other than the buff, because the buff will help put you in that right frame of mind. Right. So turn off all those other things, and then go do. I'm going to call it do nature, and it doesn't mean you have to go like look under rocks and find salamanders. But what it does mean is you have to be in the real world, the way that the people who were originally understanding this were in the real world. And I went, for example, this morning I went for a walk. I got up right at. I was going to say up at sunrise, but sunrise gets up. Well, I was up at 6, and then the sun came up at 6:20 or something like that. So I was out doing my walk this morning as the sun was coming up. And if you want to understand how the ancients thought about these things and how to progress your thought pattern to get there, it's helpful to do these things and think about how the light is coming around up over the horizon and how it's hitting you and what it's, it heats you up, and how does it do that? And when you go one direction or the other direction, and you listen to birds and you watch water flow and all these things that are natural, it's very important to do those things. It's one thing to watch a computer game simulation. It's another thing to actually go get your hands wet and skip a rock, right? That's a thing that matters. So Aristotle talked about the speed of light.
All right. What do you say?
Well, it's interesting because he quotes a guy in some of his writings where this guy is Empedocles. You ever heard of Empedocles? I never heard of him. It's like, he wasn't on my 2024 bingo card, I guess.
No.
Empedocles said it must take time for light to get from the sun to the earth. He thought it's got to take time to get there. Okay, now this, you got to keep in mind how old this is. This is like 2,500 years ago. They recognized that light traveled, that it moved from the sun to the earth.
And carried on a horse-drawn carriage across the sky. Well,
see, that's the thing is well, that's how the sun is carried, but the sun sends out, it radiates light, and you can actually feel it with your hands, right? When, like, if you close your eyes and the sun comes up, you can feel the heat on your skin. So there's some energy that's being dispensed through the light that doesn't actually come through your eyes. It's like,
yes, yep,
right, okay. So now apparently Aristotle disagreed because he didn't, he quoted this guy as saying, well, this guy says it takes time. Aristotle disagreed. Descartes, who was like, I don't know, sometime after 1500.
1500, 1600s, early
sometime
1600s.
Between 1500 and 1800. It doesn't matter to me to get the exact date. He was a long time ago. He came out with the Cartesian plane and the XYZ coordinate system that we're using for our frame of reference. So we'll give him some credit. But Descartes, like Aristotle, thought that life was instantaneous. Okay. Galileo, of course, talks about this stuff. And Fowler says that, quote, Galileo, unfairly as usual, in Two New Sciences, has Simplicico stating the Aristotelian position. Now, Galileo wrote these back and forth discussions between the simpleton guy, Simplicico, and then the other guy, I forget who his name was. But the Simplicico always says the stupid thing, and then the other guy comes in and says, no, you're an idiot. Here's how it should be. And they go back and forth. And Galileo has Simplicico talk about Aristotle's position and says, everyday experience shows that the propagation of light is instantaneous. For when we see a piece of artillery fired at a great distance, the flash reaches our eye without lapse of time, but the sound reaches the ear only after a noticeable interval. So coming up in July is going to be our Independence Day celebration. And prior to that time, and at that time, and maybe a little bit afterwards, we will see fireworks go up. And a lot of times we'll see them go up. We'll see the flash, and then you'll wait and you'll hear the boom. And now Simplicico, is that how you say it?
Simplicio.
So there you go. Thank you. Simplicio says that it has to be instantaneous because we see it before we hear it. And Galileo said, no. That's not sufficient to conclude that. The only thing that is sufficient to conclude is that light is faster than sound. Right?
Yes, that's true. Right.
So Galileo says what we should do is you should get two guys and give them each a lantern that you can open and close. Okay, so the lantern is closed. That means none of the light gets out. And you open the door and the light comes out. And what you do,
it escapes. It's like a really small cat.
Well, it's like a bunch of little tiny cats that shoot out, and they go in straight lines until what? Until there's a force on them, actually. And so they go out, and what you do is you do this little game where you say, I'm going to open my lantern. And as soon as you see my lantern open, you open your lantern.
Yep.
And then we'll time how long it takes for me to see your lantern open. And that's going to be, the lag there is going to be twice the speed, twice the time it takes light to travel that far.
Yes.
Okay.
Yep.
So he said, what you got to do, it's funny to hear how he describes it. He said, you can't just do it. You have to get two guys they have to practice it. And you have to have somebody time it so that you know how long it just takes to do the mechanics of it. Right.
Right.
Right. So you get really good at opening it when you're just practicing. And then you get a long ways away from each other and you do it and have somebody time it, and then you subtract and then divide by 2. And that's
the speed of light.
That's the there and back speed of light thing. And so Galileo said you could do this. And apparently he says he even tried it.
Well, before you started this whole thought of the podcast and everything, your thought was, and I'm sure you'll talk about this somewhere down the road in the next couple episodes, but that we inherently do not know the exact speed of light. We only know twice the speed of light.
Well, I may have.
In order to
get, I said that. Did I say that?
Oh, that's what you said. You said, or you quoted somebody saying that.
Okay, I probably quoted. Because
this is the same thing with Galileo. Is Galileo can start from point A, shoot the light to point B, and then it gets sent back from point B to point A.
Right.
And then he divides by 2. So that's the speed of light. Well, it's not like Galileo can run alongside the light beam and keep track of it with a stopwatch and say, okay, cool, you reached the second lantern. We went from point A to point B. It took...
he didn't have a lap timer, right?
Right.
Well,
there's no lap timer for light.
Okay, but it's interesting because there's an implicit assumption there, right? The assumption is that the light will travel at the same rate going there as it does coming back, and that the turnaround time...
Maybe it gets really tired.
Maybe it rests. Maybe there's like a 7-Eleven there for light. and you have a little quick gulp, and then on you go back. Well, but okay, so but those are some assumptions. And Galileo said we should do this kind of thing, and he tried this, but he didn't detect. Go figure. He didn't detect any lag, and when you see the lightning and you hear the thunder. Pretty much, don't you do that? You count 1 second, 2 seconds, 3 seconds, 4 seconds,
sure.
and you say how many
miles away.
That's how many miles away. Okay,
Yep.
So Galileo did this, and he went out there and he said, "Well, all I can figure out is that it's at least 10 times the speed of sound." That was it. That's like, I'm sorry, I can't get more precise than that. And that's like early 1600s, and he's doing this. But about 50 years later, there's this Danish guy named Ole Romer, and he was working in Paris. And the French did a lot of this stuff. They had they were the center of a lot of this kind of revolutionary astronomy and field science, I guess you could say. And he got the first real measurement of the speed of light. Okay, and it turns out that Jupiter has moons.
Yep,
okay?
Quite a few
of them. And one of the moon's name is Io, and it's spelled Io. Which to me is just a funny thing, right? And Io, okay, so if you take your telescope and you point it at Jupiter, and if you can keep Jupiter in the field because it's moving pretty quick, because the Earth is turning and all that stuff, if you can see, I've seen them, Harry, with that little cheap telescope I had from wherever I got it. I could see the moons of Jupiter, at least the ones that Galileo saw in the early 1600s.
Yeah, Ganymede, Io, two others,
Callisto and Ted the moon. So one of those moons is named Io, okay? And Io has, it gets eclipsed by Jupiter regularly, meaning Io goes behind Jupiter, so you can't see it from Earth.
Yes.
Right? And everybody knew that it did that, and it did that very regularly, and they could actually compute the eccentricity of that orbit. Okay, so the eccentricity, if eccentricity is 0 or 1, I guess I forget which one it goes. Anyway, if it's right at the decimal piece, if the decimal piece is 0, that means it's either 0.0 or 1%. It's a ratio. It's probably 1. Okay, but if you look at the like a perfect circle has perfect eccentricity. I mean, it's there's no deviation from the circle. And as you deviate, the ellipse gets stretched out a little bit, and the more stretched out the ellipse, the bigger the eccentricity. It's eccentric, okay? Like this show, it's eccentric. So they did this with Io, and Romer noticed that he would time when these, and apparently its rotation around Jupiter is less than 2 days.
Oh.
Okay. First, I read that. I was like, oh, okay, eccentricity. Okay, I'll look this one up. And wow, it's 1.76 or 1.77 days.
Really zooming around.
Yeah, because Jupiter's big,
huge.
Man.
Yeah.
And it's zipping. It's got to be really close, is what I'm thinking. It's got to be really close and moving really fast. Well, those two things go together. Otherwise, it gets sucked into the. And this is another question we have for anybody out there who's an orbital scientist. So you know where I'm going with this. What's at the bottom of Jupiter? Because it's a gas giant, right? And they say, well, it's just a ball of gas. And I was like, there's nothing in the middle. There's not like a rock or like a bunch of rocks in the middle. There's nothing on the inside other than gas. Really?
It's like a little. There's get down, you pull back the curtain. The Wizard of Oz is sitting there.
Yeah, Wizard of Oz in there, or
having a tea party with the Mad Hatter.
It's like that boot that they pull out of the pond when they're fishing. It's like but there's got to be something in there because the mass is so big with that gas pushing down. Some of that at the center,
it's pressurized. Yeah,
is it pressurized down to being a solid, and is it hot in the middle or cold? It's got to be hot, right? Pressure.
It's really cold.
Anyway, Io, spelled Io, is going around really fast once every day and 3/4. That's like every 36 hours or
42 hours.
42 hours.
40 hours.
So it's going around really fast. Okay. And he noticed that over time, the start time of that eclipse of Io got earlier and earlier and earlier than what it should be. eventually it got, after like 6 months, it was like 10 minutes early. And then it started swinging back the other way, and it got later and later and later. And eventually, about 6 months after that, it was about 10 minutes late. And then over the course of a year, it got to be 10 minutes early, and then over a year, it got 10 minutes late. So its deviation from where it should be was off. All right. And Romer noticed this thing. He said, well, 6 months one way and 6 months the other way, that's a year. And the longest delay in the start of the eclipse was when the Earth was the farthest in its orbit from Jupiter. So he realized that the light was taking time to get. So like the eclipse already happened, but he didn't see it until the light got there, right? And because it was farther away, it took the light longer. So he was like, well, it's taking longer, and
it's not instantaneous.
It's not instantaneous. And so when we're closer, we see it sooner. And when it's farther, we see it longer. We're still always delayed on it, but there's a relative delay there that's longer when we're farther away. So he knew that it was longer, but what they had to do was estimate then the size of the Earth's orbit and how far we were from Jupiter, so we could get all that estimate right. And the way you estimate that, the way they figured this out, was to measure. Okay, this is 1676. Okay, 1676. They went to measure the parallax of the Mars. Okay, so and what you do is you get two.
Yeah, you got to explain parallax.
Yeah, so if I'm looking right now at the camera here on my computer, and when I look through my right eye, my camera eclipses the knob on that door behind the computer screen. But when I look with my left eye, I can see the knob. Okay, so the apparent position of the knob depends on which eye I look through. Right. So the apparent position of the Mars depends upon where you're standing on the Earth.
Mm-hmm.
Okay, and so if you can measure the location of the Mars relative to the stars, and you can do it from two different positions on the Earth at the same time, you can get an estimate. Mind blown. You can get an estimate of how far Mars is from Earth.
Yes.
Okay.
Yep.
And because at that point, they knew the time of all the orbits of all the planets, and you can take Kepler's law to relate orbital times to orbital radii, I guess I'll call it.
Mm-hmm.
Then once you know one relationship, boom, you can solve the whole equation, the whole set of equations. All right. And they did this
in the 1600s.
1676, wearing the big powdered wigs and those fancy shoes and whatever they would,
puffy pants and jackets.
And those with the buckles on the shoe. Okay, so they did all that, and they came up with this estimate for the parallax and the thing, and the distance out to Earth, and they got an estimate for the distance from the Earth to the Jupiter to Io. All right, so they got all this stuff put together, and he estimates the time or the speed of light to be 125,000 miles per second. And the big issue, that reason he's off by that's like 3/4 of the actual value. The big issue was his computation of the Earth to the Mars wasn't very good, and he got the time it takes for light to traverse the orbit of the Earth. That's about 16 minutes, because it's 8 minutes from the sun to the Earth, and you double that for the diameter. He had that at about 22 minutes, and it should have been about 16, and you compensate for that. And the next guy redid the Mars measurements and used the same measurements of the eclipse of Io and got a number close to what we should be getting. And
wow.
It's astounding. It's astounding that they were even close on doing that. And if you have those Tufte books, Ed Tufte has some books on visual explanations. I think it's the visual explanations book, or either that or it's I think it's the visual explanations. And he talks about Galileo proving that the Earth moved, that the Copernican thing made good sense. But he talks about the Galileo and his telescope and looking at the moons going around Jupiter, and that's a really great story. If you have time to read that, pull out your Tufty books and read that. And this is the thing to note, though.
Okay.
The moon Io was discovered by Galileo on January 8th, 1610, which was like my birthday, but in 1610.
Yes, 355 years before.
Yeah, but it's on a different calendar, so I don't really know how we're going to make that adjustment. I don't really know. That had to have been Julian date, right? Or I don't know. Anyway, I'll call it my birthday. Now, Fowler notes, quote, later, Newton wrote in the Principia, for it is now certain that the phenomenon of Jupiter's satellites, confirmed by the observations of different astronomers, that light is propagated in succession, which means it takes time to get there. Okay, it travels at a finite speed and requires about 7 or 8 minutes to travel from the sun to the earth. This is essentially the correct value. Okay, this was Newton, who was writing in the late 1600s. Well, it was after this, after 1676. So it was like 1680, 1690, something like that. All right, so they knew in the late 1600s that light was not instantaneous. All right, and what we're going to do, Harry, when we get together for the next episode that we talk about this, we're going to do some more on measuring the speed of light and the remarkable experiments that these guys did to figure this out.
Precision gets closer and closer and closer and closer, right? So for the listeners out there, we have discovered that light travels.
Yep.
Right. It's not instantaneous. Light travels, and it travels at a certain speed.
Mm-hmm.
Right. So Romer estimates.
I'm going to say Romer. Yeah.
We'll say Romer. 125,000 miles per second.
Yep.
So 3/4 of the value. So we're at a 75% accurate solution here.
Yeah. And in 1728, James Brady is going to use some fancy schmancy geometry to get very close to the right answer, which is 186,000 and change miles per second. Okay.
That's pretty quick.
That is speedy, man. And we're going to get there, and then we're going to take it to what this is going to mean later. And that is going to be mind-boggling. But we will save that for a rainy day.
Yeah, and we'll save it for next time. But in the meantime, all you listeners, go out there, seek the good, live virtuously, and flourish, and enjoy the adventure of life. It's going to be a great day.